Welcome to our review for Exam 3 in Calc 3. Let's go ahead and dive in. First up here we have an iterated integral. We'd like to break this apart into separate integrals if we can. Sometimes you can work from the inside out and that's easy. That's not quite as easy as breaking it apart. See, what I notice here first is our order of integration is dy, then dx, then dz. So this cosine z in here, that's a constant with respect to the y integral and the x integral. So I can pull that outside of, remember the y integral are these limits here, and the x integral is these limits here. So I can take that cosine z, and I can pull that guy outside of both the x and the y integral. So if I do that, then I'll have integral from 0 to pi over 2, and then that cosine z is outside. And then what's left is still inside the z integral from 0 to 2x, x squared plus 1 cubed. Oh, we need an integral 0 to 1 in there. Integral 0 to 1, integral 0 to 2x, x squared plus 1 cubed, and then dy dx dz. So now all of this in here only depends on x and y. It's independent of z. So we can actually pull this integral outside of the z integral. Okay, so this thing can actually come outside the z integral. So if we do that, then we've just got the z integral by itself. So we'll have integral from 0 to 1, integral from 0 to 2x. We got that x squared plus 1 cubed dy dx. Whoops, not dx, dy dx. And then on the end we'll just have the z integral. 0 to pi over 2 cosine of z dz. So this is a Calc 1 integral, so that's taken care of. Now this x squared plus 1 cubed, that's a constant with respect to y, so that can come outside of this integral. So in the next step, this will be integral from 0 to 1, x squared plus 1 cubed. And then inside is integral 0 to 2x, dy, and then dx. So then this inside integral here, the y integral, notice that we cannot pull that outside of the x integral because of this limit of integration involves x. So this is not going to be a constant with respect to x. And then we've got our z integral on the end. So 0 to pi over 2 and a cosine z dz. Let's hold off on evaluating this. So let's go ahead and evaluate this integral inside. So this will be integral from 0 to 1. Got our x squared plus 1 cubed. And then the antiderivative here is just, this is 1, so the antiderivative is y, and that's from 0 to 2x. And then dx. So plug in 2x for y, plug in 0, and subtract. Let's bring along our z integral. Pi over 2 cosine z dz. And now we've got integral from 0 to 1, x squared plus 1 cubed. And then this is just going to be 2x. Plug in the 2x, plug in the 0, subtract 2x minus 0 is 2x dx. And then times that last integral, 0 to pi over 2 of our cosine z. All right, So now we can do a u substitution here, okay, because we've got a function here, x squared plus 1, and then its derivative is 2x right there. So that's pretty slick how that worked out. So for this one here, we're going to let u equal x squared plus 1, and then du is going to be 2x dx. So here's our du right here, and then here's u on the inside. So this will be integral of u cubed, because here's our u and it gets cubed, du. And then don't forget to change your limits of integration over. You have to plug those in to get u values. So take x equals 0, plug it in here. 0 squared plus 1 is 1, so u equal 1. Plug in x equal 1 here. 1 squared plus 1 is 2. So integral 1 to 2. And now let's go ahead and do this antiderivative. So that's going to be sine z. And we're going from 0 to 2 pi. I'm sorry, pi over 2. And now this antiderivative is easy. That's going to be u to the 4th over 4. And that's from 1 to 2. And then plug in pi over 2, plug in 0 and subtract. So that's going to be sine pi over 2 minus sine of 0. And sine of pi over 2 is 1. And sine of 0 is 0. So this is just 1 minus 0. And now we'll go ahead and plug in our 2 and plug in our 1 and subtract. So that'll be 2 to the 4th over 4 minus 1 over 4. So that's 16 fourths minus 1 fourth times 1, which we don't have to write. So it's just 15 fourths. And we got it. So that's not the only way to do it, but that's probably among the easiest ways to try and pull out those independent integrals. Just be careful, when you've got functions in your limits of integration. If instead of 2x this was a number, we would have been able to separate that apart into 3 Calc 1 integrals. So next up, we're writing an integral in polar coordinates. It's going to give the volume that's under the plane y plus z equals 4, and over the region in the first quadrant that's inside the circle r equals 2 sine theta, and outside r equals 1. So this is a circle of radius 1 at the origin. This is a circle along the y-axis, and it's got diameter 2. Give us a little bit more room here. So first of all, try and give you a picture here. To get volume, remember you integrate the function here because it's under the plane. So you're going to integrate that function over your region. So this function y plus z equals 4, if we sketch that in xyz space, it's going to look something like this. So here's z-axis. Let's see here, we've got y-axis out here. X-axis is coming straight out. And y plus z equals 4. So in the yz plane, this is just a line. In fact, that's the line z equals 4 minus y, which has a y-intercept of 4, and then your slope is negative 1. So this is going to hit at 4 on the z-axis, and if you fall 4, you're going to run 4 because the slope is negative 1. So it looks like that. And then x is left out of this equation, so this is going to vary in the x direction. So this plane looks like this. Okay, so that's that plane. And then down is, we want the volume underneath this, but only above the first quadrant region inside these two circles. Well, I'm sorry, outside r equal 1, but inside this circle. So let's sketch that region here. So r equals 1, got a circle of radius 1. And this is xy plane. And then circle of diameter 2, so that's again radius 1. So this is 1 right there, and then radius 2, or I'm sorry, y equal 2 will be up there. So circle same size, diameter 2, or radius 1. Look about like that. So just like that. And then this is our r equals 1. So we're outside of that circle. This is r equals 2 sine theta. So we know it's along the y-axis because it's a sine theta circle, and then the number out in front is the diameter. And we want the region outside this circle, but inside this one, in the first quadrant. That's going to be this region here. Okay, so let's go ahead and color in there. So that's going to be that yellow region right there. So if we take this drawing here and pull it over underneath that plane, go ahead and extend these axes here. So we're going to have that circle of radius 1. This is 4. See, this goes up to 2 along the y-axis, so that's only going to come out to here. And circle of radius 1 out to there. So you got this circle of radius 1. And then this guy is centered along the y-axis, so that's going to be out here like this. And then this region here in the positive quadrant, x is positive, y is positive, that is that region right there. Okay, so we want the volume of the solid that is above this region, but underneath the plane here. Okay, so that's the base of the solid, and this is going to, these guys are going to continue up until they hit on the plane like that, and then this guy will continue up, and this is probably going to be a curved intersection along the plane because this is curved, and then this will probably be curved out here. So that solid looks something like that. We want the volume of that guy. So what's our volume going to equal? And we're just writing the integral. We're not working it out here. So our volume then is going to be, by definition, it's the double integral of 1 over d dA. Okay, so the volume is the same thing as an area that has height 1. Okay, so your domain, length and width, area that's base, times a height 1 gives volume. Okay, so what is volume? Well, volume by definition is the double integral over the base region. Okay, and we'll call this region D here, the domain of integration of that function z equals f of xy dA. Okay, that's what volume is by definition. So then our function here is 4 minus y. So this is going to be the double integral over d of 4 minus y dA. Okay, so our domain of integration here is a polar region. So this is going to be nicer to do in polar coordinates. We want to change this to polar. So this is going to be then an integral here, 4 minus y in polar coordinates is r sine theta. And then the area element in polar coordinates here, instead of dx dy, it's r dr d theta. So now we have to set up our limits of integration, then we'll be all done. So how do you determine limits of integration? Well, you let a radial segment sweep over this region like this, and the limiting ends of that segment give the theta limits, and then the outer and inner endpoints of a arbitrary segment give the radial limits, the R limits. So, well, first we need to find that angle there. We know this one's pi over 2, but we need to find that angle there. And then we'll look at a general radial segment like that sweeps over the region. So this angle here is where the two circles intersect. So that's going to be where 2 sine theta, r equals 2 sine theta is equal to r equal 1. You set the r values equal to each other. So sine theta is 1/2, and that means theta is pi over 3. At least that's the first quadrant angle. So our theta limits on the outside here, that's going to be pi over 3. And then this one is pi over 2. That one's easy to tell. And then our r limits, the inner radius here, that radius is 1. And then the outer radius is the upper limit of integration, and that's on the r equal 2 sine theta. So this would be to 2 sine theta. Okay, so endpoints of a general segment give your r limits. The limiting values of that sweeping radial segment that touch on the domain of integration, those are your theta limits. So that's the easiest way to do that one. Alright, next we are sketching a region of integration, and we're reversing the order. And not evaluating, we're just setting up here. So here's our function that we're integrating. We're first integrating with respect to x in the x direction, so this would be x equal y and x equal cube root of y. And then we're going to integrate with respect to y from y equals 0 to y equals 1. So that's going to give us a region in the xy plane here. I'll go ahead and set up our axes here. So there's x and y. And let's see, we're starting down here, x equals y, up to x equals cube root of y. Okay, so if we cube both sides here, we get x cubed equals y. So our two curves here are x equal y, the 45-degree line, and y equal x cubed. So 45-degree line, it'll look like that. And then your y equal x cubed will look like this. So there's y equal x cubed. Which is equivalent to x equals cube root of y. And then here's our y equal x, or x equal y, however you want to do that. So first it integrated with respect to x. So the way the integral is set up now, I integrated in the x direction. So if you draw an arbitrary horizontal segment, you see that if you go from left to right, it starts at x equal y, and then the right, it ends at, forgot to put that y in there, ends at x equal cube root of y, that's here. And then let that segment sweep, so you've got a horizontal segment here, let that sweep from the bottom up to the top of the region here, and it starts at x equals 0, I'm sorry, y equals 0, and then ends up here where these two guys intersect, and that's at y equals 1. Y equal x equals y equal x cubed. We can find that intersection point here real quick. So that's how it's set up right now. So the intersection point there, x cubed equals x. Bring the x over as a negative. X cubed minus x is 0. Factor an x out. X times x squared minus 1 is 0. So either x equals 0 or x squared minus 1 is 0, x squared is 1, so x is going to be plus or minus 1. Okay, and 0 is here. And then this guy is 1, and this is also 1, because it's on 1, 1. So those are our two intersection points that are in the first quadrant. So now what we want to do is we want to reverse our order of integration. So it's going to be integral, integral, we're still integrating x e to the y over y squared minus 1. But now we want to do dy dx. So the y limits are going to go in here. So we're going to draw an arbitrary segment that varies in the y direction. X is held constant. And the lower and upper endpoints are our limits of integration. So the lower endpoint is on y equal x cubed. So this is going to be from y equals x cubed. And the upper endpoint is on y equal x. So up to y equal x. And then let that segment sweep over the region. Okay, so our region is that guy right there. So now we want to have a segment sweep over the region, an arbitrary vertical segment. So it starts here at x equals 0 and ends at x equals 1. Okay, put that guy right there. So x equals 0 is where that segment starts and ends at x equal 1. So there we're set. You don't need to rewrite the y equal x equal, that's fine. So, and we're done. We're not evaluating. Just setting it up, just reversing. Number 4, write an integral. So again, we're just doing a setup only, and I'll probably do several setups on the in-class version of the test in order to save some time. This is going to give a surface area of the portion of this paraboloid 1 minus x squared plus y squared in the first octant. So that's only going to be a portion of that. And surface area, so we need the formula for surface area here. So remember that surface area is equal to the double integral over the projected domain. So you project your surface down into the xy plane, and you integrate the partial with x squared plus the partial with respect to y squared plus 1 dA, where there's your area element. So we want to set this guy up. So first of all, let's kind of get a picture and see what's going on here. So this is a paraboloid here, and the negative inverts it, and then the plus 1 out in front is going to shift it up 1 unit. So in 3 dimensions, we've got something that looks like this. So we've got this paraboloid. It's going to look like this, and it's inverted. Okay, it hits up here at 1, and it's inverted, and that's going to actually intersect the plane in a circle, like this. And remember, this is z here, this is y, this is x. And we know that this is going to intersect in a circle because the xy plane is z equals 0, and if you set 0 here, you get 0 equals 1 minus x squared plus y squared. And if you bring that negative over as a positive, then this circle of intersection is going to be x squared plus y squared equals 1. So that's the unit circle. Okay, well, we only want the surface area over the portion of it that's in the first octant. So our domain of integration here is going to be the part in the first octant down here. So that's that piece right there, that quarter. And so the surface area, if we want, goes up on this side and hits at the apex. and then comes down on this side here. So we just want this surface area here, just that quarter of the paraboloid that's above the XY plane and in the first quadrant. Alright, so well, this is our domain of integration D, and that's actually very nice in polar coordinates, okay? So I haven't told you how to set up this double integral, so we definitely want to do this in polar coordinates. First, though, we need to find these derivatives in Cartesian coordinates. Okay, so let's go ahead and set up, this is our double integral over D, this is our region D, square root of, and this is our f of xy. So if we do the x derivative of that, so x derivative of 1 is 0, and then the x derivative of x squared is 2x, the x derivative of y squared is 0, because y squared is a constant with respect to x, and that's got a minus in front of it. So it's negative 2x. That's the x derivative, and that gets squared. And then the y derivative of our function, the y derivative of 1 there is 0, y derivative of x squared is 0, y derivative of 2y of y squared is 2y, and it's got a minus in front of it. Right? This is really 1 minus x squared minus y squared if you take the parentheses out. So the y derivative is negative 2y. And that's f sub y, it gets squared, and then plus 1. And now we've got dA. So now if you set this up in Cartesian coordinates, let's go ahead and work that through. I mean, let's say that you didn't realize that polar coordinates was the way to go. We'll set it up both ways here. So let's draw our domain of integration, which is this circle x squared plus y squared equals 1. Okay. And then here's x-axis, y-axis, and then our domain of integration right there. And then this is, if we solve this equation for y, we've got y squared is 1 minus x squared, and then take square roots. The top half of the circle is going to be the positive square root. So this will be y equals square root 1 minus x squared. And we usually like to integrate with respect to y first. So let's set this up, integral, and then let's do dy dx. Okay, so integrate with respect to y first, so we get functions of x as our limits of integration. Inside the square root, we can go ahead and simplify. This is negative 2x, quantity squared is 4x squared. And then this will be 4y squared. And then plus 1. And now if we integrate in the y direction first, so draw a y constant segment there. Lower limit is 0, upper limit is, oh, that's supposed to be a minus. Okay, said minus and wrote plus, because I've got minus down here. Take square roots on both sides. So lower limit is 0, upper limit is root 1 minus x squared, and that's y equals 0 to y equal, I did it again, goofball, me, not you, y equals 0 to y equal root 1 minus x squared. Now let that segment sweep left to right. Okay, so let that sweep over the region, starts at x equals 0, ends out here at x equal 1, right, because that circle's radius 1. So this will be x equals 0 to 1. And again, you don't have to write the x equal y equal. I'm just trying to emphasize dy dx. And then this is actually easier. From up here, you could have said, oh, well, that's easy to do in polar coordinates. Okay. If we sketch this region again, well, I can go ahead and draw the radial segment. So if we did a radial segment instead of a y constant segment, then they'd look like this. Okay, and we're setting up integral square root, and then dy dx or dA is r dr d theta. And inside here, notice that we could factor out a common 4. So we'd have 4 times the quantity x squared plus y squared plus 1. So x squared plus y squared is r squared. So underneath there is just 4r squared plus 1. And then you do your r limits first. So r limits are here. So the radius goes from 0 out to 1, because this is the circle, r equals 1. And so this will be 0 to 1. So r limits. Theta limits, let your radial segment sweep over the region. So it starts down here at 0, ends up here at pi over 2, that arbitrary radial segment. So theta goes from 0 to pi over 2. So since I just said, write the integral, I didn't tell you which coordinate system. So you could pick. So either one of these would be fine. Okay, so this figure that we've got here shows our region of integration for a triple integral. I haven't told you what the function is. I'm just concerned with your ability to switch back and forth. It's order dx, dz, dy right now. We want to write the integral with the order of integration dy, dz, dx, but we're not evaluating. So I've sketched the domain of integration here, the three-dimensional domain of integration for you to help you visualize. And let's talk about that a little bit. So let's take this integral and go ahead and bring it down. Let's spread this out a little bit here. Yeah, that's what I want. And there. And there. Okay, so what we need to understand here is that these limits are with respect to x. So this is going from x equals square root of y to x equals 1. So x equals root y in 3 dimensions, that is a parabolic sheet. It's a cylindrical surface. In fact, if you square both sides, you get y equals x squared, which is this surface here. So these limits of integration, it's saying from x equal 1 to x equal root y. So that's in this direction here. So we're integrating from this triangle is the plane x equal 1, and I've labeled it for you, over to this surface here, which is x equals root y. And then next, we're z limits. So this is z equals 0 to z equals y. So remember, what you do is you take the three-dimensional solid and you project it down on to the plane of the two variables that are left after that inside integration. Okay, so you project in the x direction onto the yz plane here. So in other words, you're looking at it from this viewpoint, and then what you see is a triangle. Okay, so you see that triangle like that, where here's your z-axis and here's y. Project on the yz plane because those are the plane of the last two variables. And then the equation of this guy here is z equals y. which is a plane in 3 dimensions, but it's a line in 2, okay, and that's this guy here, z equals y. And we're going from z equals 0, well that's just down here, so z equals 0 up to z equal y, so we're integrating like that. We're integrating in the z direction right there. And then we let that segment sweep in the y direction, and it goes from y equals 0 out here to, it's going to be y equal 1, okay, and this is y equals 0 to y equal 1. So we want to do that same kind of thing, but we want to switch the order. Okay, so we're still dealing with all the same surfaces, but we're switching our point of view here. So I'm going to go ahead and back up a little here. Okay. So we're going to do the same thing, but we're flopping that order around. So now we want to do equals integral, 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 f of x, y, z. And we're now dy, dz, dx. So dy, dz, and dx. So first we integrate in the y direction. So y varies, z and x are held constant. So we're looking at this guy from this direction here if y varies. And we want to ask, well, what do you see? Well, you're going to see this right here. Okay, but it's going to project over onto the xz plane. You project onto the plane of the remaining variables over here. And we're going to see something like that. Okay, which is this is just the line x equals 1. Okay, because it's a plane in 3 dimensions, but it's a line in 2 dimensions. And then we're taking that intersection curve, which is on y equal x squared, and we're projecting that across into the xz plane. So we really would like an equation of that curve right there. Well, if z equals y, okay, and I'm using z equals y because it's this curve here is in this plane, z equal y, and then y equals x squared. Well, then look at the two ends. If z equals y and y equals x squared, which is what happens in that intersection right there, then that gives you the curve z equals x squared. Okay, so that's that intersection curve right there. Okay, that's in the parabolic sheet z equals x squared. And that equation does not have y in it. So if you vary in the y direction, it doesn't change the equation of the parabolic sheet. So this guy right here, that is z equals x squared. So if we sketch the domain of integration now, z equals x squared looks like this. And then this is x equals 1. This is in the xz plane. And x equals 1 is right there. And so this is our domain of integration. So right there. After the first integration is done. So, okay, so if we're varying in the y direction, what are going to be our y limits here? So first we've got to do y equals what to y equals what. So if you're varying in the y direction, then you're going to go through from this surface here out to the back surface, which is the y equal x squared, so this curved surface here. So you're going to go in the y direction, and this segment, this endpoint of the segment is hitting on the back side of the surface that you can't see. So it starts at z equals y, this plane, and it ends at this guy here, which is y equals x squared. So y equals z to y equals x squared. Okay, so y equals z is the left hand, and y equals x squared is the right hand curve. Okay, and then these outer limits, dz dx, now you project it down. So this domain of integration d over there is right here. And now we're integrating in the z direction, so that's a vertical segment. And the endpoints go from z equals 0 up to z equals x squared. So this will be z equals 0 to z equals x squared. And now let your segment vary over the region, your arbitrary z constant segment. So it starts at x equals 0 and ends at x equals 1 as you sweep over that region. So this will be x is 0 to x equals 1. And again, I mean, you can write the x, y, and z equal if it helps you, but you don't have to. Okay, and now we're looking at a solid E that is bounded laterally, so on the sides by a cylinder here, x squared plus y squared equals 1, and above by z equals x squared plus y squared plus 2. So this is a paraboloid and then shifted up 2 units. And below by z equals square root of x squared plus y squared. This is a cone. The square root is a cone. If that square root wasn't there, it'd be another paraboloid. So for that solid, we want to compute the centroid of the solid, use symmetry if possible, and I'm giving you the mass as 11 pi over 6. So here, remember, centroid is the same as center of gravity if density is equal to 1. Okay, so I'm just taking rho equals 1. So well, let's sketch this region here first. So here's our z-axis, and x and y. So this is y, z, and x. And it's bounded on the sides by a cylinder, x squared plus y squared equals 1. So that's going to be a circle in the xy plane. Let's go ahead and sketch that guy here. So this is the lateral boundary. And that's also going to be up here. Right there. So this is that cylinder. So that's what bounds it on the sides. And then the region's bounded above by x squared plus y squared plus 2. So paraboloid, circular paraboloid shifted up 2 units. So this is going to be looking something like this. Get a nicer curve in there. Okay, so that's that paraboloid x squared plus y squared, shift up 2 units. And then below is the z equal root x squared plus y squared. This is the same as z equals r. So that's a 45-degree cone. So it looks like this. And it's going to intersect that cylinder in a circle, like so. There we go. Okay, so our region E it's inside this cone, but it's below this paraboloid, so it's in between those two. Okay. So let's see here. First of all, I'm going to go ahead and recall the formulas for centroid here. Well, actually, we want to use symmetry here where possible. And notice that if we take the plane x equals 0, which is this plane. No, not quite, I'm sorry. I did have it about right. This plane here, okay, that's a plane of symmetry. Cuts that solid in half. And then the YZ plane, which is x equals 0, like this, that cuts the solid in half. So the plane of the board. So x equals 0 and y equals 0 both cut it in half. So notice first of all, by symmetry, since those are planes of symmetry, the centroid's got to lie on those planes. So by symmetry, x bar equals 0 and y bar equals 0, since x equals 0, that's the YZ plane, and y equals 0, the XZ plane, are planes of symmetry. So use that symmetry when you can, so that saves you 2 integrals that you'd have to do. Okay, then we just need z bar. And then remember that z bar is, by definition, this is 1 over m times the triple integral of rho times z times dm. Okay, we know what the mass is. It's 11 pi over 6, so 1 over m is going to be 6 pi over 11. But before that, let's see here. Rho is our density, which is 1, and rho times the little mass element is going to give a volume element. So this is actually going to turn into 1 over m times the triple integral of z times dv. Okay, because the rho dm is dv. And now 1 over m is the reciprocal of this guy, which is 6 over 11 pi. And then we start setting up this triple integral here of z dv. So we can do this in whatever coordinate system we want to. And notice that you remember here that dv, what you do is you first do the z integral. Well, the easiest way to do this is because, well, no, you're finding the z coordinate of the center of mass. So what you want to do is you want to integrate first with respect to z. That's going to be that inside integral. And then the outside integral is going to be dA. So where are z limits of integration going? Well, we're going to integrate on a vertical segment, and it's going to be like this. And it's going to start on that that cone, and it's going to end up on the paraboloid. So this is actually going to go from z equals square root x squared plus y squared up to the top, which is the x squared plus y squared plus 2. Okay, and then we project down onto the xy plane, okay, because we integrated with dz first, so this dA is dx dy. But if we project down here, then that domain of integration is just the circle down here, and that's really nice in polar coordinates. Okay, so we want to try and set this integral up in polar, the double integral. So let's go ahead and do that. And notice these work out real nice in polar coordinates too. So this is then going to equal 6 over 11 pi And let's go ahead and convert this inside integral first. Square root of x squared plus y squared is r, so that's going to be z equals r. And then x squared plus y squared right there is r squared. So our upper limit will be r squared plus 2. Z, we just leave as z. Remember, x is our cosine theta, y is our sine theta, but that only applies to x and y, not z. dz. Okay, and then dA here, our area element, since we're doing polar, is going to be r dr d theta. So then you draw a general radial segment here in your domain of integration. Oh, this would be D here, our domain of integration. And that segment goes from radius 0 out to radius 1. Again, the endpoints are the r limits, so r equals 0 to r equal 1. And then the theta limits, if we let it sweep here, it's just going to be 0 to 2 pi. So it's going to sweep all the way around the circle there. So 0 to 2 pi. So that's not too bad of an integral to do here. Antiderivative, well, let's see here. This is going to be a function of r because it's got r limits in there. So we can't take it outside the r integral. However, all of this right here is independent of theta. So we could take this whole integral and pull it outside of the theta integral. So this will be 6 over 11 pi. And then pull that integral out, 0 to 1. Let's go ahead and do this antiderivative while we're at it. So antiderivative of z is going to be z squared over 2. And that's getting evaluated from r to r squared plus 2. And times r dr. And that got pulled outside of the theta integral, so the only thing that's left inside that integral from 0 to 2 pi is just d theta, or if you want, 1 d theta. So now here we've got to plug in our r squared plus 2 and plug in our r and subtract. So we got a 1/2. We actually can take that 1/2 and factor it out, cancel it into that 6 there. So that'll leave a 3. So this will actually be 3 over 11 pi. And then this will be integral from 0 to 1. R squared plus 2 comes in here and it gets squared. So r squared plus 2 squared minus plug in r squared. And then times this integral out on the end. Well, antiderivative of 1 is just theta, and that gets evaluated from 0 to 2 pi. And we got a little bit of algebra to do here, but it's not too bad. So let's see, r squared plus 2 squared. So r squared plus 2, r squared plus 2. Got to FOIL that guy out. So first term's going to give us r to the 4th. So we'll have a 3 over 11 pi in front. And then this is going to be integral 0 to 1, r to the 4th. Outer terms here, 2r squared, inner terms 2r squared, so it'll be plus 4r squared. And then last terms plus 4. And then minus our r squared. And I just realized I forgot that r outside. This r right here should be, I need a r dr right in here. See if I can squeeze that guy in there. So this is minus, give myself a little more room here, r squared. And then this gets multiplied by r dr. r dr. There we go. So this still has r dr. And then plug in 2 pi, plug in 0 for theta, subtract. So that's going to be times 2 pi. And so our pi's cancel here. And so 2 times 3 on the outside, this is 6/11 on the outside. Integral 0 to 1. Negative r squared and 4r squared combine to give us 3r squared. And then we want to multiply that r in times each one of these guys. So r to the 4th times r is r to the 5th. R times 3r squared is 3r cubed. R times 4 plus 4r dr. Okay, so now this is just power rule. So you got a 6/11 on the outside there. And let's see here, it'll be r to the 6th over 6 and plus 3 r to the 4th over 4 and plus 4 r squared over 2. That gets evaluated from 0 to 1. This 2 will go in there 2 times. Yep. Okay, and if you do the calculator work here, so we plug in 1, plug in 0, you don't get anything. So plug in your 1, you've got 1/6 plus 3/4 plus 2 times 6/11. And that gives you 35 over 22. So our centroid then is 0, 0, 35 over 22. Alright, and then last up we are going to sketch and describe the region of integration and convert the integral to spherical coordinates. So I haven't done any spherical yet. So our limits of integration, this order of integration here is dz, dy, dx. So this is z is negative root 1 minus x squared minus z squared up to z equals 0. And then y equals, and then x equals. So this is z equals, y equals, and x equals. So if z equals negative root 1 minus x squared minus y squared, and we square both sides, we get z squared. If you square the negative, you get a positive. Square the square root, it goes away. So we get 1 minus x squared minus y squared. Take these two guys, bring them over on the left as positive. We get x squared plus y squared plus z squared is equal to 1. So everything, that's a sphere of radius 1. Everything is happening inside a sphere of radius 1. So if we start sketching here, because we got to describe the region of integration, it might be helpful to sketch because it's a portion of the sphere. So z-axis up here, y here, x here, got a sphere of radius 1. It looks something like that. And then it's going to intersect so that's going to be the intersection in the zx plane. And then it's going to intersect with the YZ plane down here like that. Okay? And we are going from negative root 1 minus x squared minus y squared up to 0. So we're going from the bottom half of the sphere up to z equals 0, which is the xy plane. Okay, so we're integrating vertically on a segment like that goes from the sphere up to the xy plane, like that. Okay, well, let's look at the region in the xy plane. Okay, so that's going to be on, it's going to go from y equals negative root 1 minus x squared to positive root 1 minus x squared. So if y equals, we'll take the top, root 1 minus x squared, then you square both sides, y squared is going to be 1 minus x squared, and bring the x squared over, and x squared plus y squared equals 1, which is the unit circle. And that's the projection onto the xy plane, the plane of the remaining variables. So that's right here. Okay, so our two-dimensional domain of integration is going to be in there. So let's go ahead and sketch the domain of integration after we've done that z integration. So look like that. And we are integrating from y is negative root 1 minus x squared, that's the bottom half of the circle, to root 1 minus x squared, that's the top half of the circle. And then x is going from 0 to 1, that's the sweep of the segment. So this is x, this is y. The top here is root 1 minus x squared. The bottom half is negative root 1 minus x squared. So we are integrating on a vertical segment because our second integral is with respect to y. So you vary in the y direction. X is held constant. So we're integrating on a segment like that. Lower endpoint is negative root 1 minus x squared. Upper endpoint is root 1 minus x squared. And that's what we've got here. Let the segment sweep from 0 to 1. Okay, so that segment is going to sweep from x equals 0 out to x equals 1, which is the right half of the circle there. So our domain of integration, the two-dimensional domain of integration, is going to be right half of the circle. Okay, so on this drawing, that's x positive. Okay, so that's going to be the front half of that circle. So it's going to be here. Okay, and that little piece. So we're going from the bottom of the sphere up, but we're only doing that on the front half. So if you think of taking a knife and slicing this sphere, orange if you want, slice it in the YZ plane, so that's the front half of the sphere, then slice it in the XY plane. So we want the front half and then the bottom of the front half. So that's the front lower quarter. Okay, so that's the describe. So here we've sketched our region. So describe the region. So we want so putting these two guys together. This is going to be the front lower quarter sphere. So that's the sketch and describe. Now we got to convert to spherical coordinates. Okay, so what's this integral equal in spherical coordinates? So this is going to be integral, integral, integral. Don't have a function that we're using here. Don't have an equation of a function, but it's going to be f written in terms of rho, phi, and theta. So rho, phi, theta. So whatever the equation is in x, y, and z, we're going to plug in. X is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. So, and then remember our volume element here, dz, dy, dx, that in spherical coordinates, that's rho squared sine phi d rho, d phi, d theta. So this is our dv. So our first integral here, this is with respect to rho. So the rho integral is here. And then phi, your drop angle, is here. And then theta, your rotation. So now inside the sphere, we integrate on a radial segment. So if you draw a general radial segment for that region, it's going to go like this. And it starts at radius 0 and it ends out here on the sphere, which is radius 1, right? X squared plus y squared plus z squared equals 1 is rho squared equals 1, which is rho equal 1. The sphere is rho equal 1. So these limits are 0 to 1. And now the drop angle. Okay, so you take your radial segment, you started at the positive z-axis, and how far do you have to drop? Well, this up here is the upper half of the sphere. We're down here in the bottom half. Okay, so you're going to start your drop at pi over 2. You're going to drop all the way down to pi. Okay, remember you can't drop past pi. Your phi goes from here down to at most pi. So we are pi over 2 to pi. So our drop is going to be pi over 2 to pi. And this is phi. This is rho. And then these guys are theta. Okay, and that's what's theta equal? Well, you've got to go to the projected domain, which is here. And theta, if you let your general radial segment sweep over the region, we don't want to do 3 pi over 2 to pi over 2. We know this is pi over 2. We want to use the negative angle, so like negative pi over 2 to positive pi over 2, because that's in order. We want this to be the small angle, decreasing. As you go counterclockwise, you should increase. If we put 3 pi over 2 and then pi over 2, you're going to decrease instead of increase. So we want to use the negative pi over 2 here, and then sweep to positive pi over 2. And then we've got it. No evaluating, just changing over. So that gives you some practice in almost every type of problem, but I can do variations on these, and I've included another practice exam which has some additional types of problems in it, so make sure that you review that too.